Hey there and welcome. So, have you ever stopped to wonder why some things that are supposed to be crazy hot don't actually feel hot? Or at least they don't burn you? Well, today we're going to crack a really cool science puzzle that explains exactly that. Why a spark can be thousands of degrees, but you can touch it and be totally fine. Let's jump in.
Right, here it is, the big question. You've all seen a sparkler, right? You're waving it around, these little glowing sparks fly off, they land on your hand and poof, nothing. But here's the thing, those sparks are literally tiny little bits of burning hot metal. So how on earth is that possible? What's the secret? Okay, to solve this fiery mystery, we can't just get the answer right away. We've got to uncover a few fundamental rules of the universe first. You know, the kind of rules that explain everything from a freezing cold day in Antarctica to why sweating actually cools you down. So the entire secret, the whole thing, really just comes down to knowing the difference between two ideas that sound super similar but are actually worlds apart. It's the total energy something has versus the speed of the tiny particles inside it. Let's break that down. So, on one side, you've got internal energy. Think of this as the grand total, all the energy packed inside of an object, every last bit. And on the other side, you've got temperature. That's not the total, it's just the average speed of those particles. Just remember those two words, total versus average. If you get that, you've basically solved the whole puzzle. All right, so internal energy, what is it really? Imagine a huge box, and it's filled with millions of bouncing balls. The internal energy is the combined energy of every single ball bouncing around in there. So it depends on two things. How many balls you have, that's the mass, and how fast they're all bouncing. It's the big picture. But temperature, totally different story. Now imagine a tiny little box. Inside, there are just a few balls, but they are bouncing around like crazy, just incredibly fast. The average speed of those few balls is super high, which means it has a high temperature. But because there are so few of them, the total energy really isn't much at all. In this example just nails it. Think about it. A small glass of water and a massive lake can both be exactly 20 degrees Celsius. The average speed of their water particles is the same, but which one has more total internal energy? Well, the lake, obviously. It has trillions and trillions more water particles all jiggling around, each with its own little bit of energy. Okay, so we've got our first two clues in our detective kit. Now we just need the final piece of the puzzle. And that piece is all about understanding how energy actually moves from one place to another. And lucky for us, it always follows one simple golden rule. So this moving energy, we call it thermal energy, or, what we all just call heat. The thing is, heat isn't something an object has. It's something that gets transferred. It's literally energy on the move. And it only starts moving when there's a difference in temperature. And when it moves, it follows this one simple, unbreakable law of the universe, the golden rule. Energy always, always, always flows from a hotter object to a colder one, period. Never the other way. It's why your coffee gets cold and why an ice cube in your drink melts. Okay, we've got all our clues. We know the difference between total energy and average speed, and we know the golden rule of how heat moves. So let's go back to that sparkler and finally crack this case. First things first, the temperature of a single, tiny spark is unbelievably high. We're talking hundreds, maybe even thousands of degrees. That means the few little particles that make up that spark are vibrating and moving insanely fast. But, and this is the absolute key, look how small a spark is. It's just a little speck, a tiny flicker of light. Its mass is next to nothing. There are very, very few particles in that little guy. So what happens when you have a super high temperature, but a super tiny mass? Well, you get a very, very low internal energy. Yeah, the particles are fast, but there just aren't enough of them to carry much of a punch in terms of total energy. And that's the secret. A sparkler's spark has a really high temperature, sure, but its tiny mass means its total internal energy is way too low to actually transfer enough heat to your skin to cause a burn. Plus, whatever little heat it does have, it loses to the air around it almost instantly. And there you have it, mystery solved. Now, this whole idea isn't just a cool party trick for sparklers. This exact same science explains something really important, how we humans stay cool. It turns out your body is a total pro at using this stuff. The whole concept is called cooling by evaporation, and it's such a clever trick.
Basically, you can lower the temperature of something just by letting the fastest, most energetic particles peace out and escape. It's like letting all the hottest troublemakers leave the party.
So here's how it works for you. When you sweat, you get that layer of water on your skin. The fastest, most energetic water molecules have enough juice to break free and just evaporate into the air. And when they leave, they take their heat energy with them. So what's left behind? The slower, cooler water particles. And presto, your skin feels cooler. Brilliant, isn't it? And you see this principle everywhere. Your body does it without you even thinking. And get this, over 700 years ago, architects in Spain designed buildings with these beautiful fountains in the courtyards. The water evaporating from those fountains would literally pull heat out of the air, cooling the entire space. How cool is that? That's ancient air conditioning.
And just to see the other extreme, check out this number. This is the coldest temperature ever recorded on Earth. At negative 89.2 degrees Celsius, the air particles are moving incredibly slowly. But here's the kicker. Just like the lake, the entire atmosphere of Antarctica contains a colossal amount of total internal energy, just because there is so much of it. It's just another perfect example of how temperature alone is only half the story. Okay, so let's do a quick final recap. Internal energy is the total energy of all the particles. Temperature is just the average speed of those particles. And thermal energy is that energy on the move, always going from hot to cold. If you can keep those three straight, you've totally got this.
So the real secret, when you boil it all down, is that what we feel is hot isn't just about temperature. It's about how much total energy is actually being transferred to us. That's the difference between a tiny spark and a whole bathtub of warm water. So now that you know the rule, where else do you see it working? Think about it. Why does metal feel colder than wood, even if they're the exact same temperature? The answers are all around you.